Covalent bonds are the bonds between two nonmetals formed by the sharing of electrons. For example, we have the two nonmetals hydrogen with its 1 valence electron and chlorine with its 7. Because chlorine needs an octet to be stable and hydrogen needs a duet, they share electrons. The resulting compound is hydrochloric acid. There is an uneven concentration of electrons in this molecule due to a difference in the electronegativities of hydrogen and chlorine. Because of this, there is a dipole where the chlorine atom attracts electrons with greater force than hydrogen. Covalent bonds such as this one are weak. They have low melting and boiling points because their electronegativity difference is less than 1.7. There are two types of covalent bonds. Nonpolar covalent bonds are formed with two atoms of similar or the same electronegativity, and the electronegativity difference is less than 0.4. In this case, two oxygen atoms form a nonpolar bond. They have equal electronegativities, so the dipoles of both atoms cancel out. Due to the nonpolarity, it is not soluble and is thus a poor conductor. However, in polar covalent bonds, two nonmetals of varying electronegativities are bonded, and they have an electronegativity difference that is greater than 0.4 but less than 1.7. In this case, hydrogen and chlorine are forming a polar bond. Due to chlorine's greater electronegativity, there is a dipole pulling the hydrogen to the chlorine. Because polar covalent bonds have a relatively slight polarity, they are slightly soluble and conduct little current. Network bonds are formed in 2D or 3D structures. They have a high melting point, rigidity, and hardness. Looking at the most common examples, we have graphite and diamond. Graphite is formed by each carbon atom bonding with 3 other carbons, forming layers of atoms with delocalized lone electron pairs moving throughout the structure and having the ability to conduct current. These layers are held together by intermolecular forces, which are easy to break, such as when you are writing with a graphite pencil. Whereas in diamond, each carbon is bonded to 4 other carbon atoms, forming a 3D structure which is extremely strong. Ionic bonds are usually formed between a metal and a nonmetal. Due to a big difference in electronegativity, electrons are transferred between the atoms to make more stable cations and anions. In this example, the more electronegative chlorine rips an electron from sodium's valence level. The differing charges of these two ions creates an attractive force between them, resulting in the formation of sodium chloride. Ionic bonds, such as sodium chloride, tend to form crystal lattices, structures where the negative and positive ends of the same ionic compounds meet and form a rigid pattern. These structures have high melting and boiling points. They are also brittle because any slip in the layers will cause oppositely charged ions to meet and repel. They are also good conductors when dissolved in water, because the ions will break out of the lattice due to the attraction between the polar ends of water molecules and oppositely charged ions. Once free of the lattice, these ions are free to flow and conduct current throughout the solution. As you can tell by this diagram, ionic bonds are much stronger than covalent bonds. Metallic bonds are also arranged in a lattice. They are held together by electrostatic attraction and are ductile due to the sea of electrons constantly moving around, making the structure flexible. The sea of delocalized electrons are also excited easily, allowing for a higher conductivity and high thermal and voltage transfer due to the electrons being able to easily carry charge. Sigma versus pi bonds. Cyanic acid contains both sigma and pi bonds. Sigma bonds are present between every pair of bonded atoms. They are always the first and strongest bond formed. Without a sigma bond, a pi bond cannot be formed. Pi bonds wrap around the sigma bonds and make the atoms less flexible and unable to rotate. Sigma bonds also have a larger bond energy than pi bonds, making sigma bonds harder to break. And now, the 3D structure of cyanic acid. The shapes of these bonds represent the probability areas where bonded electrons are most likely to be found. Each bond's shape represents the overlap of 2 orbitals, one from each atom in the bond. Sigma bonds are shorter, directly connecting 2 atoms. pi bonds are longer and bent, stretching around the sigma bonds to connect two atoms. Potential energy versus internuclear distance. If two atoms are too far away, they will not interact, such as in structure 4. As the distance between two atoms decreases, there is greater attraction between the atoms and decreased potential energy in the bond. Eventually, as distance decreases, the atoms will reach the optimum bond length, shown by structure 2, where the potential energy is the lowest and the structure is the most stable. If the atoms were to get any closer, such as in structure 1, the repulsion of the electrons would make them too unstable. Thanks for watching!